Good morning, dear students. Today we are going to uh, last time we have seen calculation of delta G, delta H, and delta S for the EMF from the EMF. And at that time, how delta G, delta H, and delta S can be calculated from the by knowing the EMF of cell or by constructing the cell and how to conduct EMF or how to calculate EMF that we have been seen from the by knowing EMF. Here today we are going to start with the new point as a Nernst equation. Now see, the scientist Nernst have given the equation for the calculation of EMF of cell, and for that how this single electrode potential or cell EMF can be calculated by deriving or by having the knowledge of EMF equation which is given by or which is derived by this scientist Nernst. And at that time what it is there, by knowing some by knowing some the facts, it is possible to calculate EMF or to give the EMF equation, and from the knowledge of this EMF equation, it is possible to calculate the EMF of cell. Now see, the single electrode potential or cell EMF can be calculated. Now see, whenever we are going to write or we are going to display or to write on the paper the EMF, cell, at that time in the bracket we always write the concentration or activity of the electrolyte solution, and in that the concentration or electrolyte solution can be knowing by having the knowledge of the activity or concentration, it is possible to derive an equation for the EMF of cell. Now see, for this what it is there, from the knowledge of this it is possible to calculate the single electrode potential or the cell potential. For that, consider the EMF cell having the reaction which is taking place in the cell as A of A, B of B, giving C of C and D of D, where this A, B, capital A and capital B are the reactants, and this small a and small b are the number of reactant molecules. Here the C, capital C and capital D is nothing but the product, and here the small c and small d is nothing but what it is there, uh, number of product molecules. Now, according to the Gibbs free energy for the above equation, by having the knowledge of one-term reaction isotherm, which is given by delta G is equal to delta G naught RT ln Q, where delta G is a change in free energy, the Gibbs free energy, delta G naught is a change in standard free energy, R is a gas constant, T is a temperature, and this Q is nothing but what it is there, this ratio. Ratio means what? Activity of product upon activity of reactant, and for that purpose this Q, which is a reaction quotient or equilibrium constant, and not equilibrium constant, according to the Lee-Chatterjee principle, this for this reaction the product or this reaction quotient is given by activity of product upon activity of reactant, and for that purpose delta G is equal to delta G naught plus RT ln activity of C to power C, activity of D to power D, divided by activity of reactant A to power A raised to power A, and activity of reactant B raised to power B. Now here it is given where A of B, small a of A, small a of C, and small a of D are nothing but the activities of reactant A, B, product C, and D and delta G naught is nothing but the standard free energy change. Now we have the knowledge. Last time we have seen this delta G is nothing but minus NFE. N is a number of electron, F is a Faraday of electricity, E is the EMF, which can be determined from the what it is there by having standard potentiometer, and in that n number of electrons. Now from this equation it is possible to find how many number of electrons are taking part into the reaction. F is nothing but a Faraday's constant that we know, 96500 coulomb. E is the EMF. Here same way this delta G naught is also given by minus NF E naught. Here sorry, naught is not given. Here E naught is a standard EMF of the electrode or cell. When all the reactants and products are unity, means what, at standard state, when activity is unity and temperature is 25 degrees centigrade, at that time the equation can be written as E is equal to E naught plus RT upon NF ln activity of C to power C, activity of D to power D upon NF, activity of A to power A, and activity of B to power B. Here delta G naught, G and delta G naught should be there, and from that what it is there, okay. Here delta G and delta G naught should be there. Now here delta G is nothing but a minus NAP. Delta G naught is a minus NAP naught, and this RT ln activity of A to power A C, C to power C, activity of D to power D upon product of activity of reactant. And that's why if you divide the equation on both sides by NF, then what we get, and we make all the product RHS and LHS negative, then it will be given by E is equal to E naught minus RT upon NF ln activity of product upon activity of reactant. The equation is called as a Nernst equation, and it gives the EMF of cell at different concentration of reactants and products at and temperature. Substituting the value of R and the Faraday's constant. Now see, this is a R. R is a gas constant that we know. The gas constant has three values, and since we are taking what it is there in a calorie, and that's why it will be 1.984 calorie. Then T is a temperature. Temperature may vary. N is a number of electron, and the Faraday of electricity is a 96500. And here the ratio of product divided by product of activity of reactant. And if you calculate 2.303, 1987, if you multiply it, and if you net 4 into 10 raised to minus 4, N is given there. Then here is a T is a temperature, and by this way the Nernst equation can be derived. Simply we can repeat it. Then we know that if EMF is there, if the equation is given, if the activities are given, a cell is given. For that we can write the electrode reaction ERHS. Then here we can write the electrode reaction of the reduction electrode and oxidation electrode, and by knowing the cell or the total cell reaction at that time, we have the activities of reactant and product, and we get the knowledge of number of electron. Now according to the for the Gibbs free energy, the one-tops have given from the one-tops reaction isotherm, and it is given by delta G is equal to delta G naught plus RT ln Q. Now here Q is the reaction quotient or the reaction isotherm. Then from that, this reaction quotient, what is there? This reaction quotient is nothing but the ratio of activities of product upon activities of reactant. Here it is given. And here in this activities for the showing, this C and D are for the product, and A and B is for the reactant. This is only for the showing that this activity is for the reactant A, this activity is for the reactant B, this activity is for the reaction C, and nothing but the next one is there. This activity is for product D, and the C, D, A, and B are nothing but the number of product molecule. Now here it is given what is A of A of B, A of C, and A of D, that is activities of A, B, C, D, and delta G naught is a standard free energy change. From last time we have seen that what it is there, or we know that delta G is equal to minus NAP. Likewise, or accordingly, delta G naught is equal to minus NF E naught. And for that, this E naught is a standard free energy change. Now, since we have an equation delta G is equal to delta G naught plus RT and activities of product upon activities of reactant, and then if you substitute the equation delta G is equal to minus NAP and delta G naught is equal to minus NAP naught, then the equation will be given by minus NAP is equal to minus NAP naught plus RT ln this ratio. If you divide by minus NAP, then we will get NE is equal to E naught minus RT. This NF will be at the ratio here, and here it is a log of activities, the ratio of activities of product upon activities of reactant. Now here you look, R is a gas constant. The value in the calorie, there are 5 values for the gas constant: 1.987, 8.314 joule. Then it is in a liter atmosphere. Then one may express this value R, a value of R in cc atmosphere also. But here, for our calculation purpose, we will use the value of R in calories. Here T, the temperature may vary. N is a number of electron and F is a Faraday's constant, and the Faraday's constant is nothing but 96500. And if you calculate this ratio, 2.303 into 1.987 upon 96500, then it comes out to be 1.984 into 10 raised to minus 4 into T upon N log of this ratio. Now, by having the knowledge of this Nernst equation, it is possible to calculate the single electrode potential as well as the cell EMF. Now, how, by taking an example, how the single electrode potential can be calculated, or how the cell EMF can be calculated, we will display an example. Consider the electrode. What it is there? CD, dipped in a solution of CD2 plus, having activity A is equal to 0.01 molar at 25 degrees centigrade. First of all, you write the electrode reaction whenever it is given to calculate the EMF of cell or electrode. Now see, in the examination, it is always asked. What it is asked? Electrode or cell will be given, and from that electrode or cell, the concentration or activity may be given, and from the activity or by having the knowledge of activity or concentration, and by having the knowing or by knowing the equation, Arrhenius equation, then it is possible to calculate the EMF of single electrode potential or EMF of cell. Now see here, if you write the electrode reaction, here say oxidation process is taking place. Here CD is giving what it is there, CD solid giving CD2 plus in a solution or in a ionic form, having activity A is equal to 0.01. Now see here, this N in that equation is nothing but the 2, and for that purpose here N is equal to 2, activity of CD is equal to 0.01. Then activity of CD, if you substitute the activity and N value, then it is given by E naught CD minus 2.303 RT upon 2F log of activities of this CD2 plus upon activity of CD solid. From table, last time we have seen standard electrode potential, and in that the different values of standard electrode potentials are given, and from that if you take the standard electrode potential of CD2 plus, then it is found that it is nothing but it is a 0.40, and therefore these are the standard means of delta G naught, and for this CD2 plus it is the value of 0.40, and from that by substituting the value of this 0.40, now this 403 and the value at the last may not have the any some the calculatable value, and for that there we have write 0.40. Now what it is there, sorry, here then we have the value 0.403, and from the table it is nothing but 0.403 volt, and that's why ECD, EMF of this electrode, is equal to E naught oxidation of this electrode minus 0.059. Now see here what it is there. There last time we have been calculated. What we have been calculated here, the temperature is taken as a 25 degree centigrade. What it is there, temperature is taken as a 25 degree centigrade, and by having the knowledge of all this and by dividing, the value comes out to be 0.059. If you calculate it or if you do it, then it will comes out to be 0.059 log of activity of CD2 plus. Now here 0.403 in the minus 0.059 upon 2 log of 0.01, because the concentration or activity is nothing but 0.01. Now here what it is there, what do you what is this 0.01? The 0.01 is nothing but 10 raised to minus 2, and log of 10 raised to minus 2, remember well, log of 10 raised to minus 2, and if you have the value of log of 10 raised to minus 2, it is always minus 2, because log of 10 to base 10 is nothing but the 1, and if you calculate it, then it will be what it is there, minus 2, and for that purpose 0.403, now this 2 and this 2 will get cancelled, and the minus will get plus, and that's why the value of it will be 0. If you make the sum, then it will be 0.462 volt. Now if the reduction process is taking place, then what will happen? Then same way the calculation will be there. Here in the reduction process, what will happen? The CD2 plus taking 2 electrons and will give the what it is there, CD solid. Here the reaction is given. If the reduction process takes place, then this CD2 plus having activity A is equal to 0.01 and takes 2 electron and will give the CD solid. And if you substitute it into the equation of Arrhenius equation, then ECD is equal to E naught CD. Here we have to write the reduction. Here we have also mentioned the oxidation, and minus 0.059 upon 2 log of activity. Here what will happen there? Here activity of solid CD divided by activity of CD electrolyte or solution having number of electron 2 plus, and that's why here it is, we know that the activity of solids, pure liquids, pure gases are always taken to be 1 at 25 degrees centigrade. Remember well what it is there, activity of pure solids, pure gases and pure liquids are always equal to 1, and here for that, here the activity of CD solid should be equal to 1, and here also the activity of CD solid is equal to 1, and that's why our equation will become CD is equal to minus. Now here why minus we have written? Because here it is nothing but what is there, it is the reduction potential, and for that purpose what it is there, we know that, or we have seen that oxidation potential is equal to reduction potential, but the sign will be opposite. If suppose oxidation potential is positive, then same value of reduction potential will be there, but the sign will be negative. And for this purpose, what is that? 0. Minus 0.049403 minus this one, and this is nothing but 10 raised to minus 2. And if from denominator it goes to numerator, then accordingly, according to the rules of logarithm, it will be 10 raised to 2. And for that purpose, the log of 10 raised to 2 is always equal to 2, because log of 10 raised to 1 is a 1, and for that purpose log of 10 raised to 2 is a 2. And for this purpose minus 0.403, here it is 0.59 upon 2, and is log of 10 raised to 2 is nothing but 2. And that's why if you make the sum, then it will comes out to be 0.462 volt, and the sign is minus. Here you see oxidation potential by having calculating by the Arrhenius equation, it comes out to be 0.463. It is a positive and it is a negative, because it is a reduction potential, and the potential is sum but the sign is opposite. And by this way the single electrode potential can be calculated. Accordingly, if the cell is given, then the how the cell EMF can be calculated, that here we will see by having an example. Consider the cell, this lead dipped in a solution of lead 2 plus, having activity of the lead. Then here it is, what it is there, here it is a calomel electrode. Now at the left hand side, or negative electrode or oxidation electrode, what happens there? Oxidation process will happen, will giving the electrons. Then accordingly the electrode potential will be given as E lead oxidation, E nod standard electrode potential of lead oxidation, minus 0.203 RT upon NF, means of 2, because here 2 electrons are involving into the reaction, log of activity of lead 2 plus. Similarly, the another electrode is a calomel electrode, which is a reduction electrode, and we have the reaction last time. Then accordingly here E reduction is equal to E nod reduction 2.303 RT upon NF, and log of activity of chloride ion raised to 2 into activity of Hg raised to 2 upon activity of Hg2Cl2 solid. And we have seen that just now, or the right now, we have been quoted that the activity of pure solids and liquids at 25 degrees centigrade are always taken to be 1, and for that purpose here we have not written that activity of Hg and activity of this, because this is a pure solid, this is a pure liquid, and for that their activities are 1, and that's why here only the activity of chloride ion will be there. Now if you want to calculate the EMF of cell, what it is there, if you want to calculate EMF of cell, then what one has to do, one has to make the sum, because we know that E cell is equal to E oxidation plus E reduction, and therefore from the equation, adding the equation, first of all you will have to write the cell reaction, and from that afterward you will have to write the equation for cell EMF. And therefore what it is there, the reaction here, what it is there, this lead solid, then what it is there, this Hg2Cl2 solid. Now here lead 2 plus ion, then here 2Hg plus 2Cl minus ion, having activity of Cl minus ion. This is nothing but the net cell reaction or total cell reaction. And since we have been added the electrode reaction, and therefore EMF of cell, right now we have been said that is it is nothing but the sum of oxidation potential minus reduction potential, and therefore the equation for oxidation potential is this, the equation for reduction potential is this, and therefore we are going to make the sum. Now since these both Enod PB upon Enod calomel is the standard electrode potential, therefore they can be, or the sum can be made. And after that, according to the rules of logarithm, here it is 2.303 RT upon 2F. 2.303 RT upon 2F is a common, and therefore we can take it common. And what it is there, you look, there will be the product of what it is there, activity of, whenever the rules of logarithms are there, whenever the product of log is there, or sum of log is there, at that time we can write as a product, or we can write as a sum. And for that purpose, here if the sum is there, log of activity of Pb2 plus log of activity of Cl minus ion, then what it is there, this according to rules of logarithm, it can be written as product of activities. And by having this, we can write the equation E cell is equal to E naught PB plus E naught C minus 2.303 RT upon 2F log of activity of lead 2 plus into activity of Cl minus raised to 2. And therefore, we can write this equation like Enod cell also Enod PB oxidation plus Enod standard electrode potential calomel reduction, and this is nothing but the total E cell, and that's why E cell is equal to Enod cell minus 2.303 RT upon 2F log of activities of this product. From table, if you take right now at the beginning we have seen the electromotive series, or the table where the standard electrode potentials are mentioned, or standard electrode potentials are given, and from that table the values are known. Then Enod cell is equal to 1.265, and this one is a 0.268. Then Enod cell comes out to be 0.3945 volt. Now, if suppose activity of lead is 0.1 and activity of Cl minus is a 1, then if one normal calomel electrode is there, then what will happen there? Heating or substituting this concentration into this equation, then our equation comes out to be what it is there, minus 0.3945, here it is, then 0.059 upon 2 log of 0.1 into 1 raised to 2. We know that 1 raised to 2 is nothing but a 1. If you take 1 raised to 2 means what? 1 into 1 into 1. And for that purpose, the value comes out to be what if you calculate it, if you make the difference of these two values, here minus will get plus, here it is a plus, and if you take the sum of these two values, it comes out to be 0.424. And by having, means what? By having the knowledge of Arrhenius equation, if the electrode or cell is given, then it is possible to calculate the single electrode potential or cell EMF. At the beginning, we have seen how to determine or how to experimentally find the value of single electrode potential. At that time, what it is there, we have to take this unknown electrode, we have to couple it with another known electrode, then we have to connect to the potentiometer. If potentiometer is not available, if the electrode is given in its concentration of electrolytes are given, then by having the knowledge of this Arrhenius equation, it is possible to calculate the single electrode potential. And if the cell is given, the cell EMF can also be calculated by having Arrhenius equation without constructing or without having the potentiometer or without connecting to the potentiometer. And therefore, by calculation, it is possible to calculate the single electrode potential as well as cell EMF. Then next thing is there, since here we have seen what it is there in the equation, this is the reaction quotient, and if this reaction is in equilibrium, then how equilibrium constant of this reaction can be calculated by from the given cell, then it can be calculated as, and therefore the equilibrium constant of a cell reaction, if the, remember well, if that reaction is an equilibrium reaction, then equilibrium constant can also be calculated by having the knowledge of, remember well, by having the knowledge of standard electrode potential or cell EMF or electrode EMF. Now here, since we know that आपल्याला माहिती आहे डेल्टा जी नॉट इज इक्वल टू हा एन इंटू एफ इंटू ई नॉट. ई नॉट इज अ स्टँडर्ड इलेक्ट्रोड पोटेन्शियल. तसंच द फ्री एनर्जी सुद्धा आपल्याला माहिती आहे डेल्टा जी इज इक्वल टू डेल्टा जी नॉट प्लस आर टी एल एन के. तो जो काही रिॲक्शन कोशंट होता, तो रिॲक्शन कोशंट जर ती रिॲक्शन इक्विलिब्रियम असेल तर तो क्यू इज इक्वल टू के ए, इक्विलिब्रियम कॉन्स्टंट. And for that, what it is there, for this काय हा इक्विलिब्रियम कॉन्स्टंट. अँड आपल्याला माहिती आहे मग डेल्टा जी नॉट इज इक्वल टू मायनस आर टी एल एन के. आपण ज्यावेळेस थर्मोडायनामिक्स ऑफ फ्रॉम ई एम एफ, त्यावेळेस आपण इक्वेशन पाहिलं होतं डेल्टा जी इज इक्वल टू मायनस आर टी एल एन के. आणि म्हणून हा डेल्टा जी नॉट काय मायनस एन एफ ई नॉट, आणि त्यामुळे हे इक्वेशन काय होईल, हे इक्वेशन मायनस एन एफ ई नॉट इज इक्वल टू मायनस आर टी एल एन के. आणि म्हणून ई नॉट इज इक्वल टू हा ई नॉट इथे आणि हा आर टी सॉरी एन एफ जर इथे डिवाइडला घेतला तर काय होईल, आर टी अपॉन एन एफ हा एल एन के. मग ई नॉट इज इक्वल टू हा आर ची व्हॅल्यू टाकली, टी ची व्हॅल्यू आहे इथे, कारण की हा जो काय आहे हा नॅचरल लॉग आहे, आणि लॉग टू द बेस्ट कन्वर्ट करायचे असेल तर कसं काय करावं लागेल, 2.303 ने मल्टिप्लाय करावं लागेल. हा आर, हा टी, हा एन आणि एफ, आणि इट विल बी गिवन बाय लॉग ऑफ के. आणि म्हणून बाय हॅव्हिंग द नॉलेज ऑफ काय, विदाउट हॅव्हिंग एनी abstraction और डिफिकल्टीज, जर का तुम्हाला त्या हे दिलेलं असेल इलेक्ट्रोमोटिव्ह सिरीज वरनं स्टँडर्ड इलेक्ट्रोड पोटेन्शियल दिलं असेल आणि तो इलेक्ट्रोड दिलेला असेल किंवा सेल दिलेला असेल, तर तुम्हाला त्याचे इक्विलिब्रियम कॉन्स्टंट हा काढता येतो. काय करायचे त्यासाठी, इलेक्ट्रोड रिॲक्शन लिहायची. इलेक्ट्रोड रिॲक्शन लिहिलं तर तुम्हाला त्याचं तो जो काही इक्विलिब्रियम कॉन्स्टंट आहे तो तिथे तुम्हाला कॅल्क्युलेट करता येतो. आणि या स्टँडर्ड ईएमएफ वरनं इथे का लक्षात, जो आपण इलेक्ट्रोमोटिव्ह सिरीज मध्ये आहे त्या सिरीज मध्ये मधून हे माहिती आहे तुम्हाला, आर माहिती आहे, टी माहिती आहे, एन माहिती आहे, एफ माहिती आहे, हा इक्विलिब्रियम कॉन्स्टंट तुम्हाला कॅल्क्युलेट करता येतो. इथे लक्षात. समजा हा सेल दिलेला आहे कुठला, आता या सेलच्या बाबतीत पाहू. याचं हा सेल Zn deeped in a solution of Zn2 plus, हा कॉपर deeped in a solution of copper 2 plus इलेक्ट्रोलाइट, हा ऑक्सिडेशन इलेक्ट्रोड, हा रिडक्शन इलेक्ट्रोड. मग यांची इलेक्ट्रोड रिॲक्शन वरनं सेल रिॲक्शन काय राहील, हा Zn काय होतो, आयनिक फॉर्म मध्ये जातो आणि 2 इलेक्ट्रॉन देईल. हा कॉपर काय करेल, 2 इलेक्ट्रॉन ते जे रिलीज झालेले ते घेईल आणि सॉलिड फॉर्म करेल, आणि त्यामुळे Zn गिविंग Zn2 plus 2 इलेक्ट्रॉन आणि कॉपर 2 plus 2 इलेक्ट्रॉन विल गिव्ह द कॉपर सॉलिड. आणि त्याच्यावरनं आपल्याला ही सेल रिॲक्शन लिहिता येईल. आपण आतापर्यंत एवढं पाहिलं, त्याच्यावरनं डायरेक्टली द सेल रिॲक्शन ही असेल. मग या इक्वेशन वरनं आपल्याला इक्विलिब्रियम कॉन्स्टंट कसा काढता येईल, हा इक्विलिब्रियम कॉन्स्टंट काय असेल, ऍक्टिव्हिटी ऑफ Zn2 plus इंटू ऍक्टिव्हिटी ऑफ कॉपर divided by activity of Zn solid इंटू ऍक्टिव्हिटी ऑफ Cu2 प्लस. आणि आपल्याला माहिती आहे सॉलिड आणि लिक्विड ची जर ते प्युअर फॉर्म मध्ये असतील 25 डिग्री सेंटीग्रेडला ती ऍक्टिव्हिटी किती असते, यांची व्हॅल्यू किती असेल, सॉरी कॉपर सॉलिड याची आणि याची काय असेल, ऍक्टिव्हिटी 1 असेल. आणि म्हणून ऍक्टिव्हिटी ऑफ Zn2 प्लस अपॉन ऍक्टिव्हिटी ऑफ Cu2 प्लस. आता बघा हा इनॉड सेल जर आपण त्या इलेक्ट्रोमोटिव्ह सिरीज वरनं या Zn इलेक्ट्रोडचं स्टँडर्ड इलेक्ट्रोड पोटेन्शियल पाहिलं आणि या कॉपर इलेक्ट्रोडचं स्टँडर्ड इलेक्ट्रोड पोटेन्शियल पाहिलं, तर ते साधारणतः तिथून आपल्याला त्याची व्हॅल्यू मिळू शकते. आणि ती किती असेल, या Zn इलेक्ट्रोडचं इलेक्ट्रोड पोटेन्शियल स्टँडर्ड इलेक्ट्रोड पोटेन्शियल 0.7618 आणि या कॉपर इलेक्ट्रोडचं स्टँडर्ड इलेक्ट्रोड पोटेन्शियल 0.337 आणि ती व्हॅल्यू येते 1.0988 व्होल्ट. आता आपल्याकडे हे इक्वेशन आहे E नॉट इज इक्वल टू 303 अपॉन लॉग ऑफ के. त्यावरनं आपल्याला आपण ही व्हॅल्यू के ची व्हॅल्यू या इक्वेशन मध्ये जर सबस्टिट्यूट केली है के ची व्हॅल्यू या के ची व्हॅल्यू इथे, तर काय होईल बघा इथे E नॉट सेल अपॉन 0.295 कारण की आपण 0.059 अपॉन 2 आर टी आणि एफ यांची व्हॅल्यू टाकली तर ती किती येते, टेम्परेचर 25 डिग्री सेंटीग्रेड आणि त्याच्यात 273 मिळवलं ऍब्सोल्यूट करताना, तर ते 298 होईल. हे काय झालं 1.987 इंटू 278 येतं का लक्षात, 273 प्लस 25 डिग्री सेंटीग्रेड ते जर तुम्ही मिळवलं तर हे 302, देन हा 2, देन हा एफ 96500. दिस विल कम्स आउट टू बी, हा जो काही रेशो येईल तो रेशो येतो काय येईल तो 0.2095 and from that log of k is equal to आपण ही व्हॅल्यू कॅल्क्युलेट केलेली आहे 1.0988 अपॉन 0.295 आणि म्हणून log of k is equal to 37.16 हा प्रॉडक्ट जर घेतला तर. आता हा काय आहे लॉग. जर या के ची ऍब्सोल्यूट व्हॅल्यू काढायची असेल तर मग काय करावं लागेल, तुम्हाला अँटी लॉग घ्यावं लागेल. येतं का लक्षात, काय घ्यावं लागेल, अँटी लॉग घ्यावं लागेल. आणि मग 16च्या जर तुम्ही 0 मध्ये लॉग पाहिला, अँटी लॉग पाहिला आणि हा 37 काय जाईल 10 to power 37. अँड देअरफॉर जर तुम्हाला या इलेक्ट्रोडचं किंवा सेलचं जर स्टँडर्ड ईएमएफ तुम्हाला टेबलवरनं मिळू शकतात, डाटावरनं मिळू शकतं आणि त्यांची ऍडिशन सबट्रॅक्शन किंवा त्यांचा जो काही रेशो असेल की त्यांच्या अकॉर्डिंग टू द इलेक्ट्रोड रिॲक्शन अँड बाय हॅव्हिंग द सम टोटल नेट सेल रिॲक्शन किंवा इलेक्ट्रोड रिॲक्शन, तर त्याच्यावरनं आपल्याला इलेक्ट्रोडची किंवा त्या सेलचं काय काढता येतं, इक्विलिब्रियम कॉन्स्टंट हा काढता येतो. आता या इक्विलिब्रियम कॉन्स्टंटचे काही सिग्निफिकन्स आहेत. काय या इक्विलिब्रियम कॉन्स्टंटचे काही सिग्निफिकंट आहेत. या इक्विलिब्रियम कॉन्स्टंट वरनं ती रिॲक्शन होते का नाही हे आपल्याला ठरवता येतं. म्हणजेच काय, इफ टू इलेक्ट्रोड पोटेन्शियल डिफर्स वाईडली के इज हायर अँड प्रोपोज्ड रिॲक्शन इज पॉसिबल. काय माहितीये का, जर त्या इलेक्ट्रोडचं स्टँडर्ड इलेक्ट्रोड पोटेन्शियल वेगवेगळं असेल, बघा हायर डिफर्स हायर म्हणजे त्या दोघांमध्ये डिफरन्स असेल आणि ती जी काही रिॲक्शन आहे ती रिॲक्शन मग त्यावेळेस काय होते, पॉसिबल होते. आणि त्यावेळेस इफ के इज लोअर द रिॲक्शन इज नॉट पॉसिबल. त्याच्यावरनं आपल्याला ठरवता येतं, कशावरनं, व्हॅल्यू ऑफ के वरनं ती रिॲक्शन होईल किंवा होणार नाही. आता दुसरं त्याचं सिग्निफिकन्स आहे त्या कशावरनं, ही जी काही व्हॅल्यू आली या व्हॅल्यूवरनं आपल्याला अजून दुसरं काय ठरवता येईल, हाय व्हॅल्यू ऑफ के in case of Daniell cell indicates that the reaction is virtually complete. काय, जर का व्हॅल्यू ही जास्त असेल कशाची, इक्विलिब्रियम, बघा इथे काय आली इक्विलिब्रियम कॉन्स्टंटची व्हॅल्यू काय 1.445 इंटू 10⁻37 अशा पद्धतीची व्हॅल्यू जर का आली तर मग ती रिॲक्शन झालीये का नाही झालीये आणि ती रिॲक्शन कंप्लीट झालीये का नाही झालीये. जर का तुम्ही त्या डॅनियल सेलचं के पाहिला, इक्विलिब्रियम कॉन्स्टंट पाहिला किंवा त्याचं व्हॅल्यू पाहिली तर ती अतिशय आहे आणि त्याच्यावरनं ती रिॲक्शन पूर्णतः घडते, पूर्णतः होते असं आपल्याला त्याच्यावरनं गृहीत धरता येतं किंवा आपल्याला ठरवता येतं. नंतर तिसरं सिग्निफिकन्स आहे व्हेन द इक्विलिब्रियम विल बी अटेन्ड, म्हणजेच त्या रिॲक्शन वरनं जर समजा सेल दिलेला आहे, त्याची इलेक्ट्रोड रिॲक्शन दिलेली आहे, ती रिॲक्शन काय केव्हा घडेल किंवा किती वेळामध्ये तिचं इक्विलिब्रियम स्टेजला जाईल किंवा ती पूर्ण होईल हे आपल्याला ठरवता येतं. फॉर एक्झाम्पल सपोज हा टिटॅनियम इलेक्ट्रोड येतं का लक्षात, आणि हा टीन इलेक्ट्रोड, म्हणजेच काय हा सेल टिटॅनियम डीप्ड इन सोल्युशन ऑफ Ti2+ आणि Sn डीप इन सोल्युशन ऑफ Sn2+. आता हा टिटॅनियम जेव्हा काय होतो आयनिक फॉर्म मध्ये जाईल त्यावेळेस त्याचं काय होतं, त्याची व्हॅलन्सी किती आहे +1, आणि त्यामुळे आपल्याला इथे काय होईल, टिटॅनियम विल गिव्ह Ti++1 इलेक्ट्रॉन, याचं लक्षात. परंतु आता इथे Sn ला किती इलेक्ट्रॉन लागणार आहेत, 2 इलेक्ट्रॉन लागणार आहेत, त्यामुळे आपण काय करू, हाफ Sn2+ घेऊ. हाफ Sn2+ +1 इलेक्ट्रॉन विल गिव्ह 1/2 Sn सॉलिड. अशा पद्धतीची ही सेल रिॲक्शन तुम्हाला काय करता येईल, लिहिता येईल. आणि त्याच्यावरनं ही रिॲक्शन जर रिडक्शन रिॲक्शन असेल सॉरी हा सेल दिस रिॲक्शन ऑफ Sn2+ ion बाय थॅलियम अँड इक्विलिब्रियम कॉन्स्टंट जर ती हॅपन होत असेल तर इक्विलिब्रियम कॉन्स्टंट काय होईल, ऍक्टिव्हिटी ऑफ, बघा इथे काय आहे, ऍक्टिव्हिटी ऑफ Ti+, हा ऍक्टिव्हिटी ऑफ Ti+, आणि ऍक्टिव्हिटी ऑफ Sn2+ रेस टू 1/2. व्हॉट इज दर Sn2+ रेस टू 1/2, आणि हा रेशो येतो साधारणतः काय 2.163 जर आपण कॉन्सन्ट्रेशन घेतली तर, का लक्षात. आणि त्यावरनं ऍक्टिव्हिटी ऑफ Ti इज इक्वल टू के इंटू ऍक्टिव्हिटी ऑफ Sn2+. याचाच अर्थ असा झाला की ही रिॲक्शन इक्विलिब्रियम स्टेजला जाण्यासाठी आपल्याला टीआयचं कॉन्सन्ट्रेशन किंवा ऍक्टिव्हिटी किती घ्यायला पाहिजे हे सुद्धा आपल्याला ठरवता येतं. Therefore, the equilibrium will be established when activity of Ti ions becomes equal to 2.163. आता हा 10⁻³ आहे, त्यामुळे मल्टिप्लाय जर केलं तर काय होईल, इथे 2.163 × 10⁻³ आहे तो रेशो. आणि मग ही रिॲक्शन जर पूर्णत्वाला न्यायची असेल तर हा या टीआयची व्हॅल्यू किंवा टीआयचं ऍक्टिव्हिटी किंवा टीआयचं कॉन्सन्ट्रेशन किती पाहिजे हे सुद्धा आपल्याला काय करता येतं, कॅल्क्युलेट करता येतं, आणि किती कॉन्सन्ट्रेशन घ्यायला पाहिजे हे ठरवता येतं. अँड देअरफॉर हिअर वी हॅव सीन, आपण पाहिलं की इक्विलिब्रियम कॉन्स्टंट जर तुम्हाला ईएमएफ माहिती असेल किंवा स्टँडर्ड ईएमएफ माहिती असेल तर तुम्हाला त्या रिॲक्शनचा इक्विलिब्रियम कॉन्स्टंट सुद्धा कॅल्क्युलेट करता येतो. बघा मग आता ईएमएफच्या व्हॅल्यूवरनं आपल्याला डेल्टा जी कॅल्क्युलेट करता येतो, ईएमएफच्या व्हॅल्यूवरनं आपल्याला डेल्टा एच कॅल्क्युलेट करता येतो, ईएमएफच्या व्हॅल्यूवरनं आपल्याला डेल्टा एस कॅल्क्युलेट करता येतो, म्हणजेच काय, गिब्स फ्री एनर्जी, नंतर एन्थाल्पी, नंतर एन्ट्रॉपी, आणि आता इथे नवीन एक कॅल्क्युलेशन किंवा एक व्हॅल्यू आपल्याला कॅल्क्युलेट करता येते जर का तुम्हाला स्टँडर्ड ईएमएफ किंवा ईएमएफ ऑफ सेल हे माहिती असेल तर. आता आपल्याला वेगवेगळ्या प्रकारचे इलेक्ट्रोड पाहिजेत, येतं का लक्षात. देर आर डिफरंट टाइप्स ऑफ इलेक्ट्रोड, आणि त्या इलेक्ट्रोड वरनं आपल्याला कुठल्या कुठल्या प्रकारचे इलेक्ट्रोड्स असतील हे आपण आज दुपारच्या लेक्चरमध्ये आपण परत कंटिन्यू करणार आहोत. आणि दुपारी म्हणण्यापेक्षा साधारणतः 3 नंतर आपण या जे काही सेकंड लेक्चर आहे हे सेकंड लेक्चर घेणार आहोत, आणि त्यामध्ये आपण वेगवेगळ्या प्रकारचे कुठले कुठले इलेक्ट्रोड्स आहेत दॅट इलेक्ट्रोड वी विल सी, आणि त्या इलेक्ट्रोड्स वरनं आपल्याला कशा पद्धतीचे सेल करता येतो दॅट वी विल कंटिन्यू. अँड टुडे वी विल टेक one more lecture at the noon. And here we will wait, or here we will stop our lecture. I will display the time schedule for the another lecture afterwards, and at that time we will see the different types of electrode, and here we will stop our lecture, and we will continue the second lecture today also, today at the noon.